This is an overview of a section of the College Trigonometry, corrected edition by Stitz and Ziegler. The section I'm overviewing is section 10.3, the 6 circular functions and fundamental identities. For the most part, I will be covering what's in the book. However, I will be covering a couple of extra things that might make things a little bit more understandable. All right, let's move on. So the 6 circular functions, supposing theta is an angle plotted in standard position, and P, x, y is a point on the terminal side of theta, which lies in the unit circle. So we are, let's see, where'd my pen go? There we go. We're on the unit circle, standard position. This is the point P, which is x, y, and this is the angle theta. We already know cosine theta is x, and sine of theta is y. So what's new in this section? We have secant, S-E-C, secant theta. Secant theta is 1 over x. Since cosine of theta is x, you might notice that secant is 1 over cosine as well. So secant is 1 over x, of course, provided x not equal to 0. All of these statements, provided x not equal to 0, here provided y is not equal to 0, x, y, this means that we're going to have domain restrictions when we look at these as functions. There will be certain places where they are undefined. And that will make some strange things happen when we go to graph these as functions later on in this book. But for now, this is pretty straightforward. Now, secant is 1 over x. The reason for the 1 is actually the unit circle. So we'll get into what these look like when we go beyond the unit circle. Cosecant, CSC, is 1 over y. That is related to the sine. Tangent is y over x, and it's tan. And that is a combination of both sines and cosines. And then cotangent, COT, is x over y. These are the 6 basic trig functions that we'll be working with the rest of the semester. There are some others that are related to these, that these are the basic ones. We'll need to be able to work out these 6 functions or these 6 trigs for all the different unit circle values that we know and all the different quadrants, and that's part of what we're going to cover. All right, let's take a look at that. Now, with the reciprocal and quotient identities, we see the relationship between, for example, secant is 1 over cosine. Again, provided cosine is not equal to 0. And if cosine equals 0, secant is undefined. And we will have some problems with the domain because of this. Cosecant is 1 over sine, provided sine is not equal to 0. Tangent is sine over cosine. And cotangent is cosine over sine. So these are the reciprocal identities. We see secant is 1 over cosine, and cosecant is 1 over sine. There is another one, that would be tangent theta equals 1 over cotangent theta, and cotangent theta would be 1 over tangent theta. And the ones that they gave us, we could also rewrite them in terms of the other function, like cosine theta is 1 over secant theta, and sine theta is 1 over cosecant theta. So they're not all listed, and the tangent and the cotangent are written as quotient identities, cosine over sine, but they also exist as reciprocal identities in their own right. Okay, let's move on. So here we have the common sine and cosine values. This part is actually not from this section. I pulled it from another section. But we have 0 degrees or 0 radians. Cosine is 1, sine is 0. We have this nice table, and this book has suggested that you memorize this. And we have one video, one of the help videos in this section, that covers a method that you can use your left hand and the fingers to help you remember these. There are some other ones. They also suggest that the tangent and the cotangent values should be memorized. This is starting to look like a lot of memorization, so it would be nice to have another technique. You eventually want to have some of these memorized, if not all of them, and that will become from familiarity. But let me show you something that's a nice way to do this. So first off, you write the number 0, 1, 2, 3, 4. Below that, you do the same thing, but starting at 4 and decreasing. 4, 3, 2, 1, 0. Put a square root around that, and the whole thing over 2. Now, a square root of all these numbers does not mean anything mathematically. It is just, oh, I'm trying to fix the 4. It is just, wow, that didn't work. Let's make a new 4. This is just another way to have these numbers written down. So this is 0 or 0 degrees. This is 30. Let's see. This is going to be really hard to write. I'm going to have to zoom in while I write this just for a moment. Might help you anyway. Let's see. I'm not going to be able to erase some stuff. Okay, so this one is pi sixths, or 30 degrees. This one's pi fourths, or 45 degrees. And pi thirds, or 60 degrees. And finally, pi halves, or 90 degrees. And this will top sine, and then below that, cosine. Okay, let me zoom back out. And show you how this can be used. So it's easy to set up. I suggest you take a moment and pause this video and rewrite this from memory. It's very easy to set up. Just make sure you're using sine and cosine, not the other way around. Starting at 0, sine. Okay, so we see, for example, cosine of 30 degrees is square root of 3 over 2. This same information is right here. Cosine 30 degrees, we get 3, but that's all under the square root, so square root of 3 over 2. Sine of 30 degrees would be square root of 1 over 2. Sine of 90 degrees, you go to sine and 90 degrees. Square root of 4 is 2. 2 divided by 2 is 1. So in this way, you can get all your sines and cosines, and it's a table. It's not in your head, but it's something you can create on the spot when you're doing a test or a quiz and be able to get these numbers out, which is really a nice thing to do if you don't have them memorized yet. The 45-degree angles, like cosine of 45, square root of 2 over 2, that would be 45 cosine. Here's your square root of 2 over 2. Beautiful. All right, so how can this be used for our tangent and our cotangent? First off, we could work one of these out. So for example, I want to work out tangent 30 degrees. So let me move this up a little bit. There we go. Tangent 30 degrees. Tangent 30 degrees. This is sine 30 degrees over cosine 30 degrees. This is the definition of tangent, sine over cosine. Sine of 30 degrees, we can look up. It's 1/2, and cosine is square root of 3 over 2. We can then invert and multiply the denominator. So we're doing a little algebra to reduce. And we have 1 over square root of 3. Now you might notice they have square root of 3 over 3. So there's a little bit more work to be done. That work looks like this. Well, let's do it this way. Nope. There we go. If we multiply by square root of 3 over square root of 3, the denominator is square root of 3 times square root of 3 is 3. That's how we rationalize the denominator. This book makes it a point of emphasis for you to rationalize your denominator. A lot of teachers are okay if you don't. You will have to know your teacher. Ask them, find out. The numerator is 1 times square root of 3 is just square root of 3. So that's how they get that value, square root of 3 over 3. So you can solve for tangent 30 degrees using the basic definition, sine over cosine. Let me show you another way. You can see why, because of all this work, why they suggest that you memorize this table, because it's a lot of work. However, in this technique, sine over cosine, 1/2, you get, let's see, we're doing tangent 30 degrees, which is sine 30 degrees. Sine 30 degrees is 1/2. There it is. And cosine of 30 degrees is square root of 3 over 2. And then the halves cancel. The halves will always cancel when you're doing tangent or cotangent. So you can just look right here. Sine over cosine. Sine over cosine. Square root of 1 over square root of 3 is 1 over square root of 3. So you can jump straight to this point. That information is right there. So this format makes it a very nice, quick way to get sines and cosines and tangents. Even cotangents, you just have to do them in the opposite order. I will show one of those in a moment. However, when you're using this, it will still give you 1 over 3 square roots. It will still give you the square root in the denominator, and you will still have to do this rationalizing denominator to get the book's answer if you're comparing with the book. Okay, now what if we wanted to find cotangent of 30 degrees? So to get cotangent, you have to know that what cotangent is. Cotangent is cosine over sine. Now whether you write that out or you just know it, you have to be able to know that it's the cosine on top. So when we're doing cosine 30 degrees, we have square root of 3. That's on top. And the over 2 cancels, so we're just doing the numerators basically. Hope that makes sense. Sine of 30 degrees, 1. So tangent was 1 over square root of 3. Cotangent is square root of 3 over 1. It's actually square root of 3 over square root of 1, but the square root of 1 reduces. So you can use the same table for your tangent and cotangent values. So this is another technique for you to have the unit circle values for sine, cosine, and now we see tangent memorized, or at least easily accessible. This is a very nice tool. I suggest that you be able to recreate it in like 10 seconds quickly. Now, why are some of these values undefined? So if we look at tangent of 90 degrees, why is tangent undefined at 90 degrees? Well, tangent is sine over cosine. Well, square root of 4 is 2, divided by square root of 0 is, well, square root of 0 is 0. 2 divided by 0 is undefined. You cannot divide by 0. So because tangent is a dividing by cosine, every time cosine is 0, pi halves, 90 degrees, tangent will be undefined. Cotangent, cosine over sine. Anytime sine is 0, that's at 0, then cotangent would be undefined. So we now have a nice way to get the tangent and cotangent values and sine and cosine values. Now as far as secant and cosecant, well, you just take the sine and reciprocal them. Let's see if we can, as far as examples go, I'm not doing too many examples in these overall videos. You will see the examples in the other videos that we have on Canvas. All right, let's move on for now. All right, Theorem 10.7, Generalized Reference Angle Theorem. The value of the circular functions of an angle, if they exist, are the same up to a sine of the corresponding circular functions of its reference angle. So this works for cosine, sine, secant, cosecant, tangent, and cotangent. The only thing that we really have to worry about, therefore, is what is the reference angle, and then for the plus minus choice, what is the quadrant of the terminal side. So if I'm looking for sine 300 degrees, I have to figure out first off, where is 300 degrees? And 300 degrees is about right there. Now the reference angle is always the angle measured off of the closest x-axis, so this would be the reference angle. And that would be 360 degrees minus 300 degrees, 60 degrees. So that's our reference angle. And they're calling this alpha. So for 300 degrees, the reference angle is 60 degrees. So this theorem states that sine of 300 degrees is going to equal plus or minus sine of 60 degrees, which is square root of 3 over 2. So is it plus or is it minus? What we see is this one ends up in quadrant 4. There is a really nice tool. All students take calculus. What this is, all students take calculus. Now, if you happen to be doing trigonometry for something other than calculus, you can state all suckers take calculus, but that's personal preference. I like all students take calculus. This tells you which of the three major the three being sine, tangent, and cotangent. Sorry, let me say that again. Sine, tangent, and cosine, the three major ones, the basic three, sine, tangent, and cosine. Which one of them is positive in which quadrant? The A stands for that all sine, tangent, and cosine are positive in quadrant 1. In quadrant 2, only the sine is positive. Cosine and tangent are negative. In quadrant 3, only the tangent is positive. Sine and cosine are negative. And in quadrant 4, where we are, only the cosine is positive. So sine and tangent are negative. Well, we're dealing with sine, and we're in quadrant 4 where only cosine is positive, so we know the sine is negative. So we end up with negative square root of 3 over 2. So once again, when we have a problem where it says sine 300 degrees, we have two jobs to do. First job, what is the reference angle? Drawing these angles makes it a little bit easier to get reference angles. If they're in radians, reference angles are trivial. I'll show that in a minute. And once you figure out what the reference angle is, in this case 60 degrees, then which quadrant is it in so you can tell if it's plus or minus. This is how you use this theorem. It's a very useful theorem. There's another quick example. If we wanted to do, let's say, secant of 7 pi sixths. So our two jobs, first off, we have to figure out what the reference angle is. Now 7 pi sixths, let's figure out where it is. Pi sixths, if you're counting pi sixths, that would be 1 pi sixth, 2 pi sixths, 3 pi sixths, 4, 5, 6 pi sixths, 7 pi sixths. So this is 7 pi sixths. That's the measure that we're working with. And the reference angle is this one. When you're dealing with a sixths, the reference angle is pi sixths. No fancy business, that's just it. The reference angle alpha equals pi sixths. I don't care if it's 7 pi sixths or 11 pi sixths or 19 pi sixths. If it's a sixths, the reference angle is pi sixths. Radians makes this super easy for reference angles. If it's a pi fourths, 7 pi fourths, 3 pi fourths, any kind of pi fourths, negative 13 pi fourths, the reference angle is pi fourths. If it's a thirds, reference angle is pi thirds. If it's a halves, reference angle is pi halves, but those are done, the quadrangles are done a little bit different. Easy though. Okay, now that we have our reference angle, we can also spot that it's in quadrant 3, where all students take calculus. Tangent is the only positive. Secant is the reciprocal of cosine. So it will have the same sign, plus minus, as the cosine does. So since tangent's positive, cosine is negative here, the reciprocal will also be negative here. So we're going to get a negative answer. Let's now go into our knowledge of cosine. What's cosine of pi sixths? Cosine of pi sixths is square root of 3 over 2. You either have that memorized or you use the little chart I just showed you. Cosine is square root of 3 over 2. Secant of 7 pi 6 will therefore be negative and 2 over square root of 3. So it's the reciprocal. You take the square root of 3 over 2 and you make the reciprocal 2 over square root of 3. We'll rationalize that. The negative comes from that we're in quadrant 3. In fact, maybe we can, oh, that's good. I like that. All right. So then rationalizing, multiply by square root of 3 over square root of 3, and we get our final answer, 2 square root of negative 2 square root of 3 over 3. This gives you an idea of how you're going to evaluate sine, cosine, tangent, secant, cosecant, cotangent of all of the angles that have reference angles 30, 45, 60, 90 degrees. In any quadrant, you've got two jobs to do. What is the reference angle? And what quadrant are you in, so you know what plus or minus. If you're dealing with one of the reciprocal identities, the reciprocal functions like secant, take your cosine and flip it, and then worry about the sign and making it pretty, rationalizing, etc. All right, moving on. This book suggests that you memorize all 9 of these forms. The Pythagorean identities. First off, let me just go back to a really basic picture. That should be a right triangle. Now it is. Theta, x, y, r. X squared plus y squared equals r squared. That's Pythagorean theorem. If I divide by r squared everywhere, I now have, I'm going to put this in parentheses, x over r squared plus y over r squared equals 1. X over r is cosine theta. So we have cosine squared theta plus, and y over r is sine squared theta equals 1. And there's your fundamental Pythagorean identity. That one is worth memorizing. Absolutely memorize it, know it well. It comes up a lot. In fact, it's used to find the rest of these. Okay, so now that we have a quick proof of the fundamental Pythagorean identity, let's work with it. There we go. I got a little space. So starting with I'm having trouble writing all of a sudden. Let me try this again. Cosine squared theta plus sine squared theta equals 1. These other common alternative forms are very useful to recognize, and you will see them when you do identities that are coming up later in this section. They are not necessarily worth memorizing because of this simple thing. If I were to subtract sine squared theta from both sides of this equation, I would get cosine squared theta equals 1 minus sine squared theta. And there we have it. That's not worth memorizing because it's one step. If instead I subtracted cosine, here I go, I can't write again. I can do math, but I can't do English apparently. Let's try this again. If I subtract cosine squared theta. And this is a little messy, but you guys are trig students, so I'm not worried about you following steps. I know you can. You would end up with sine squared theta equals 1 minus cosine squared theta. And we have arrived at the other one. Those are not worth memorizing because they're easy to get. Just know the basic one. Sine squared plus cosine squared, or cosine squared theta plus sine squared theta equals 1. Okay, so what about the rest? Why not memorize the rest? They look interesting. Well, they're definitely different. This one has tangent and secant, this one has cotangent and cosecant, but they're the same one as before. Let me demonstrate. Try to delete some of this stuff. There we go. So, if I were to divide by the first one, cosine squared theta, what I would get is cosine squared divided by cosine squared is 1 plus. Now here, sine squared, don't worry about the squares for a minute. Sine over cosine is tangent. So sine squared over cosine squared would be tangent squared. Tangent squared theta. 1 over cosine is secant. 1 over cosine squared would be secant squared. And here we have arrived at this other form. Notice it says provided cosine theta equals not equals 0. The step we just did, dividing by cosine squared theta, cannot be done if cosine theta equals 0. So we have to specify that cosine is not equal to 0 to even do this step. Now, the common and alternate forms, the same kind of manipulation. If you move this tangent over, we'll get secant squared minus tangent squared equals 1. There it is. If you move this 1 over, we'll get tangent squared equals secant squared minus 1. There it is. You can just play around with these all day long and get different versions. In fact, how about this version? Oh, that's this version. Never mind. Okay, so that's not worth memorizing because it's just one quick step from the original, although you can memorize it. Let's get rid of these. See if I can all at once. Nope. There we go. Last step, you can probably imagine what I'm going to do. If I divide by sine squared theta, obviously sine cannot equal 0 to do this step. Let's assume it's not. We get cosine over sine is cotangent. Cosine squared over sine squared would be cotangent squared theta. Plus sine over sine squared over sine squared, 1, equals 1 over sine is cosecant, CSC. 1 over sine squared would be cosecant squared, CSC squared theta. And we have arrived at this other third Pythagorean identity. It's all based on the very first one. I recommend that you practice starting with the basic first one and getting the alternate forms of the first one, then converting it to the second one, and you can work with the second one to get its alternate forms, convert it to the third one, and etc. It's a lot easier than memorizing everything, in my opinion, but maybe you have a photographic memory and this is just wasting your time. I hope not, though. All right, let's move forward. Because of the last fundamental Pythagorean identities, this book makes mention of the Pythagorean conjugates. Now, a conjugate is nothing fancy. If you had a plus b, then a minus b is conjugate. That's that. So we have 1 minus cosine and 1 plus cosine. 1 minus sine, 1 plus sine, secant minus 1, secant plus 1, etc. These are all just conjugates. What they do, if you have 1 and you multiply by the conjugate, and you'd obviously have to have an equation or something so you could do this in a way that makes sense mathematically, multiplying 1 plus cosine theta to both sides of an equation, for example, it would give you both of these that would then multiply together to make one of the alternate forms of the Pythagorean identities. So you can basically pass from 1 minus cosine, which is kind of messy, in an equation or an identity using multiplying by a conjugate, and pass from there to something that's easier to work with in all the different formats. If you happen to have cosecant theta minus cotangent theta, you could get to 1 if you were able to multiply by the conjugate. So this is useful in applications of specifically identities. So it's something to consider when you don't know what else to do. Try multiplying by the conjugate to see if it makes something that you recognize in an identity form. And that's all there is to this part. Let's move on. Okay, now we get to a part of trigonometry that is, on one hand, very fun, like a puzzle, a Sudoku puzzle, something that you just work on and find out, and there's always a way to solve the identities, even though they're not really solving. Verify, though. And on the other hand, causes panic in some students because they don't know what to do next. The thing about identities is there isn't necessarily an obvious next step every time, but as long as you take an appropriate step, a step that makes sense mathematically, you can always get from point A to point B. So let me explain a little bit. What an identity is, the simplest identity I can think of, how about 1 equals 1? That's an identity. It's always true. Unlike x equals 1, which is only true if x equals 1, 1 equals 1 is always true. So we will be dealing with identities. For example, tangent theta equals sine theta secant theta. Is that true? Well, it is true, but it's your job to show. If it says verify the identity, verify, they're telling you it's an identity and your job is to show that it's an identity. With 1 equals 1, it's really clear that the left side is identical to the right side. Therefore, this equation is an identity equation because they're identical. X equals 1. X is not always identically 1. It can be any value. It's a variable. So this is not an identity. This would be called a conditional equation. Tangent theta equals sine theta secant theta. Is that true or not? Well, it is because I told you it's an identity. So it is true. How do you show that it's equal? Now, what you can't do is work on both sides of the equation simultaneously. You cannot divide both sides by sine. Nothing on both sides. You are stuck with working either on the left side or on the right side, or maybe a little bit on the left side and then a little bit on the right side, and until you finally get the left side and the right side to look the same. And for the most part, you'll be looking for, do I know any identities? For example, on this problem, I know what tangent is. Tangent is sine theta over cosine theta. So I have worked on the left side. I did not do anything on the right side at that same time. Now, on the right side, I know sine theta is one of the basic ones, but I know secant is 1 over cosine theta. That's the definition of secant. That's a reciprocal identity. The tangent equals sine over cosine. That would be a quotient identity. We can now see the left side, sine over cosine, sine theta over cosine theta. And the right side, we can use basic multiplication of fractions. Multiply the top together and get sine theta. Multiply the bottom together and get cosine theta. We've verified this identity. It's obviously equal now. It wasn't clear before, but using some substitutions and some basic algebra, we now have shown that both left and the right sides are identical. This is what it looks like to verify an identity. So, notice some of the things they say. If you find yourself stuck working with one side, like on the left side, there's nothing else I can do with sine over cosine, I already had it at tangent, then start to work on the other side. See if you can find a way to bridge the two parts of your work until they're equal. Multiply numerator denominator. Now this is a special technique. Multiplying the numerator and denominator by the same number is a technique that is really multiplying by 1, and you can just do that on the left side somewhere, or just on the right side. You won't see anywhere in this list, multiply both sides by something. You cannot do that. So some other things they suggest, use reciprocal and quotient identities. That's what worked for us on this one. Add adding fractions with common denominators. Use Pythagorean identities, and we have 9 of them to work with, etc., etc. So these strategies are great, and yet when you get to the identities, it's just a matter of what do you recognize to do first, and then do it. And don't make any algebra mistakes, and just keep working, keep moving forwards. If you get stuck on one side, move to another side. Okay, there are some more examples of this in the other videos. Let's move on. If we are not on the unit circle, if we go beyond the unit circle, we've already seen sine and cosine. For example, sine theta is y over r, or you might see it as y equals r sine theta. These are both true. Or cosine theta equals x over r, or you might see it x equals r cosine theta. These four things, or really two, are what the sine theta and cosine theta look like. When you're on the unit circle, we knew sine theta was just y, because r was 1 on the unit circle. So this part we've already seen on the unit circle. But on any size circle, we then get this formula for sine. Which one should you memorize? Well, I would suggest this one, because if you're on the unit circle and you let r equal 1, you then reduce to the other formula. So the other formula is just a reduction of this one. It's a special case. So I would rather you know the main general formula, this one, because from that you can get the other. Now in terms of the y over r, sine, secant is 1 over sine. So you would take sine and you'd do the reciprocal, r over y. R is the square root of x squared plus y squared. That's just the Pythagorean theorem, essentially. Tangent is sine over cosine. If you did sine over cosine, the r's would cancel and you get y over x. There we go. And cotangent is the reciprocal of tangent, x over y. So these are pretty basic. You still just basically need to know the sine and the cosine, and you can work the rest of these out. Now, trigonometry, the root of the word, trig is from Greek for triangle, angle, and trigonometry, metrics is from measuring. So it's about measuring all the things on a triangle. So since we're in trigonometry, I think using the triangle instead of the unit circle is often a better way to go, and that's what the next part is about. Let's take a look at it. So here we have a general triangle. It's not specific radius, it's just A, B, C, and theta. Now we have in the past seen sine theta is B over C, cosine theta is A over C. We've also seen this in terms of opposite over adjacent. I'm sorry, that's wrong. Opposite over hypotenuse. Let's get that right. There we go. And cosine is adjacent over hypotenuse. Okay. We now see that tangent is B over A. Make a little more, well, let me just rewrite it somewhere else. Tangent is B over A. Tangent is B over A. Now in terms of opposite, adjacent, hypotenuse, from the theta's perspective, oh, I didn't even draw a theta. As a math teacher, if I see that someone forgot a theta, I have to take points off. So I better get it right. Comma tangent theta, there we go, equals B over A. And from the perspective of theta, B is opposite. and A is adjacent. So this would be opposite over adjacent. So these are the big three: sine, cosine, tangent. The same big three that I used when I did the all students take calculus. There is a little tool that's very useful. SineCosine. And for whatever reason, it sticks in people's head when you say SineCosine, because it's like soak your toe. SineCosine. SineCosine tells you this formula, this relationship for sines and opposite adjacent hypotenuse. Let me demonstrate. Sine is opposite over hypotenuse. Here we go. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So here we have SineCosine, a very easy way to remember this. Setting up a triangle and being able to solve problems using triangles instead of the Pythagorean identities makes often a much faster and cleaner solution. Let me take a look if I have a good example for you. All right, let's do this one. So I'll just do tangent. Find tangent theta if secant theta equals -4 and theta is in quadrant 2. Well, knowing secant, find, let's try a D on that one. What do you think? There we go. Find tangent. There is a relationship, one of the other forms of the Pythagorean identities for sine, cosine, tangent, secant, all those others. Let's see. Sine squared theta plus cosine squared theta. Since I told you you don't have to memorize all 9 of those that we did before, how can I make a tangent? This problem is asking about tangent. How do I make a tangent? And will it work to get a secant as well? To make a tangent, I divide by cosine squared. That'll make tangent, because sine over cosine is tangent. So what does that give us? That gives us tangent squared theta plus 1 equals 1 over cosine of secant squared theta. Beautiful. So there is a relationship between tangents and secants. So knowing secant is very convenient to finding tangent. I made up an easy one. But we still have to solve for tangent. So if I just subtract that 1, I can get to there. So tangent squared theta equals secant squared theta minus 1. So we go up to our problem, and tangent squared theta equals secant squared theta minus 1. What we can do is basically plug in -4 for secant. Now the squared notation, it's important to understand what it means. It means secant squared. So I'm going to go back to secant squared notation, and I'm plugging in the -4, because that's what secant is. That was how it was given. So that gives us tangent squared theta equals 16 minus 1, 15. So tangent theta equals plus or minus. That happens when you take a square root. Square root of 15. But is it plus or minus? Well, what quadrant are we in? Let's see, we're in quadrant 2. That should be a quadrant 2. That's looking like a 4. This is quadrant 2. It is a lot easier to write on paper than on an iPad, but I'm doing the best I can, I promise. Quadrant 2, all students. Only sine is positive, so tangent is negative. Great, we just worked out that tangent is negative, because only sine is positive in quadrant 2. So our final answer is negative square root of 15. So this, we can use our fundamental Pythagorean identities and all students take calculus and all that good stuff to find tangent if we know secant. Now if they ask for find cotangent, we'd still get to tangent and flip our answer. If they asked us to find sine. With secant, we can get to tangent, and then we have, that would be harder. Let me show you the triangle approach to this. I think it's much easier. I need to erase a bunch of work. Hopefully it'll let me erase almost everything. Not everything. It's not going to let me get that little sine plus cosine. Okay, fine. All right, let me show you the way I prefer. After all, this is trigonometry. Quadrant 2. If I make a triangle in quadrant 2, call that theta. Now secant is 1 over cosine. So, toa. Cosine is adjacent over hypotenuse. There it is, adjacent over hypotenuse. So secant is hypotenuse over adjacent. Let me put over 1 on this problem, because we're finding that secant hypotenuse over adjacent, that's going to be -4 over 1, or 4 over -1. It is 4 over -1. So if I were to ask you, what is secant theta, you would want to think secant first I'd like you to think, there we go. All right, and then I'd like you to think that cosine is adjacent over hypotenuse. That would be -1/4. Cosine would be adjacent over hypotenuse. Cosine, adjacent over hypotenuse. -1/4. So secant would be flip that, -4 over 1. Beautiful. So this information is the same as this information. In fact, it's the same including the quadrant 2, because this terminal side of this is in quadrant 2. We're just using the reference angle because we're smarter than having to do that, because it's not even a triangle. All right, so once we have this in place, now we can work with just the basic, for a minute, let me call that y. -1 squared plus y squared equals 4 squared. That's just the Pythagorean theorem now. That gives me y equals plus or minus square root of 15. The work, that would be 16, that would be 1, subtract it, that would be 15. Square root plus or minus, we've gone through this work, it just looks simpler now. And now, is it plus or is it minus? Well, this -1, I know it's negative because this direction from the origin is left. That's towards the negative x values. So this is -1. Hypotenuse, by the way, is always positive. Don't ever mess that up. It's always plus. That's how I knew the minus went with the 1. The hypotenuse is always positive. -1. Well, this y value is up. Since it's up, it's positive. Square root of 15. Okay, great. So now we have the entire triangle set up. This problem that I asked you to do was just find tangent, but the problem in the homework says find all 6, or find the remaining 5. There are 6 total. There's sine and its reciprocal, cosecant, cosine and its reciprocal, secant, and tangent and its reciprocal, cotangent. There are 6. So they'll ask you to finish all 6, so find the remaining 5. It's hard to do with identities. It's easy to do with triangles. Here we go. What is secant? Secant, this is all secant stuff, and we've finished. What's tangent? Tangent is opposite over adjacent. Opposite over adjacent. So our final answer would be, make a little more room. Say that's the one. Tangent theta would be opposite over adjacent, or just negative square root of 15. I think that's more basic mathematics, and it's also graphical, it's visible. So I would much prefer that form than doing the identities. Although the identities are great for when you're just getting used to the identities. They're a great way to remember them by continually reviewing them, by having to use them over and over. It just takes a lot more time. All right, let's move on. This book uses what's called extended interval notation sometimes. So take a look at this for a minute. This does not look very pretty. u from k equals negative infinity to infinity, parenthesis, and this little k's and pi's. And if you ever see that, don't freak out. Instead, understand what it means. What it means, so if I let k equal 0, that would be gone, and that would be gone. And I'd be looking at pi halves and 3 pi halves. I'd be looking at this one right there. Parenthesis, pi halves, comma, parenthesis. That's it. Okay. So if k equals 0, you get that piece. What if k equals 1? I wrote 1, negative 1. Let's try negative 1. If k equals negative 1, then this will be negative 2 plus 1. That would be negative. So we'd be looking at negative pi halves. And this one would be 1, negative 2 plus 3 is 1, 1 half. That's this one. So by letting k be all different numbers, we're just getting all these different intervals. K equals negative 2, we get this one. K equals negative 3, we get this one. K equals 1, we get this one. And on and on and on and on forever. The unions come from this. So this is a fancy way of writing an infinite number of unions of intervals. That's a lot of information. You can see why this notation is convenient. It's a lot easier than writing all that. But now what does all this mean? So from pi halves to 3 pi halves is just this. From negative pi halves to pi halves is just this. But notice, pi halves is not included. We do not have a hard bracket here or here. So there's a hollow dot over pi halves. But everything else around it is included until we get to negative pi halves or 3 pi halves. So this is essentially all real numbers except for those few that are being spaced over, that are being gapped, being skipped. So we have all real numbers except for these few, which is probably easier written in this format. All values of t except for plus or minus pi halves, comma, plus or minus 3 pi halves, comma, plus or minus 5 pi halves, comma, dot, dot, dot. That's the notation I prefer because it's pretty clear and straightforward. But the book, well, you have this one. That's kind of a crazy thing. And yet, hopefully now you understand what it means when you look at that and you go, oh, let's just let k equal 1 and 2 and 3 and see if we can pick up the pattern, and then we know what they're talking about. Okay, that's extended interval notation, a brief view. Moving on. If we treat all of these 6 basic trig functions, the big 3, cosine, sine, and tangent, and their reciprocals as functions, f of t equals, so instead of theta, we use t, and we start to recognize these circular functions, the domains and ranges. So for example, cosine and sine have infinite domain, and the range is between -1 and +1. You can try around with your calculator. I don't care what mode, whether it's degree or radians. If you plug in anything you want and hit sine, you will never get a number outside of this range. It'll always be at smallest -1 and at the largest +1. That's it. Anything you want. You can plug anything you want into sine. The domain is all real numbers. You plug anything you want into there. But you only get these kind of numbers out. Same with cosine. Secant is different. In fact, everything you get out of cosine is about what you don't get out of secant. It gets everything else, except for the -1 and +1. So you'll get large numbers, 2, 3, 4, 10, 5,000, billion. You just won't get numbers in between -1 and +1. You'll get everything else, including -1 and +1. And the domain, here we have this really fun notation, is everywhere except for, let's think about this, secant is 1 over cosine. Where is cosine 0? At all these values. So secant's domain is everything except for those, which we know this accepts those values. So this is a fancy way of saying everywhere except for where cosine is 0. Cosecant is 1 over sine, so the domain is everywhere except for where sine is 0. The range is everything basically except for the range of sine, except for those 2 spots. Tangent, you can put everything in tangent except for where denominator cosine is 0. That's the same as secant. This has a divide by cosine, this has a divide by cosine, same domain. The range is all real numbers, everything. Tangent hits every spot. You can play around with your tangent button on your calculator and you'll get all sorts of different numbers out. And cotangent, which has a divide by sine, will have the same domain as this cosecant that has a divide by sine. All values except for the pi values, pi, 2 pi, 3 pi, 4 pi. And the range again is all real numbers. So this gives you an overview, although it wasn't brief, it gives you an overview of section 10.3 in this book. And I hope that helped. There are still some more examples and videos showing examples of doing these different problems, and then of course the homework. All right, great, thank you.